I have here with me Brian Evangelista. He is my footings guy. Glenn, he's my columns guy. Elizabeth, she's my slabs woman. We have Marlon over here. He is my stirrups person. And then Alan is my beam guy. Today we're talking about Nordstroms of San Jose. So real quick, problem definition. For you, we are trying to build a 3-story Nordstrom building while meeting the safety constraints as outlined by ACI, AISC, and for safety purposes while minimizing the cost. Now, of course, all pictures here are artistic interpretations. Don't take any of them for facts. They are not to scale. There will not be planes flying over your building at all times, and people will not double park. However, they help you show what we're trying to do. So lot selection, real quick. We had 3 different selections, and with those, we had these objectives that we wanted to meet. Price per square foot. Demographics, ease of access, size, demolition, and cost of permits. We wanted to maximize all those. We found that was what was important to get a good Nordstrom. So what we did here was we had all of our first place, we got 3 points. These are the ones in green. Second place got 2 points, and third place only got 1 point. We added these points together to get a total points. As you see right here, 14540 Almond Expressway got 18 points. Therefore, we chose that as the best lot for Nordstroms with the most income could be had. So frame and beam locations. We have here our artistic interpretation. First, we had frame A. This is our beams and our columns. Within that, we have floor 1, floor 2, floor 3, and the roof. And we have beams 1, 2, and 3. Today, we'll be showing you floor 3 highlighted in green. We also show you the column. We call the column, we highlighted in blue. So first, a slab location. You see this is frame A. I'm going to do some magic. I'm going to rotate the building, and I'm going to show you where frame B is. And within frame B, we have this slab, and right there is the slab we were designing for you today. So loading assumptions. So first, we have our live load. In our design report, we have that down as people. Of course, they can be more than people. They can be live people, dead people. They can be chairs, shoes, storage, whatever you'd like. So we have our highest live load is beam 2, floor 3, 1.44 kips per linear foot. Let's take those live loads off, and now look at what we have. Now we have the rain load up on top. We only have that for the roof right here, with the highest rain load being beam 2 on the roof, and that's because it has a cantilever part as well. Let's take the rain loads off. Now everything we have left is our dead load, the things that we cannot move. We cannot move the windows, can't move the doors, the walls, the slabs. So all that left, and the highest dead load we have is 3.25 on the roof, and also on the cantilever is 3.18 kips per linear foot, which is close second. We put all these loads together, get a factored load. We use an ACI 9-1, 9-5. The only two that really govern were 9-2 and 9-3 shown, and the highest factored load 6.12 pounds per linear foot, or kips per linear foot, my apologies, and that's what we will design. So now to design loads, put all those into SAP, did some magic, did some different criterias, different loading assumptions, and we got these are our worst moments out of all the different cases that we did, with the highest moments being right here, -440 and 327 kips per foot. Then our frame A for our shear right here. Once again, same location is our highest loading. And then for the column, we have floor 3 in the MX, roof for the MY, and then the P as on the floor 1 is where our greatest loads are. So we designed for all those on one column. So now I'll hand this over to Alan, my beam guy.
Alright, here's our floor 3 design view, and we've been primarily focusing on the 3 beams on the bottom on grid line 6. Our 2 beams on the left and opposite corners are L beams, and beam in the middle represent our T beam. We're designing for single reinforcement, and here's our cross section for T beam, and our L beam right here, and our max positive moment for T beams is about 3,500 kip feet, and the L beam is about 1,700 kip feet. Likewise, for the negative moment, we have our T beam and L beam, the same cross sections, and dimensions we use to calculate our max moment for negative. Our max negative moment is also 603 kip feet. Here's our elevation view of floor 3. You see our beam 1, 2, and 3. And we have our negative max moments at corners against the base of the columns. We have a positive moment in the middle of the beam. And we see our moments associated with each moment, negative and positive. And for each of the moments, we have our area of steel needed, or number of bars needed to support each moment. Likewise, for beam 2, we have our moments and our reinforcement required to support the load. And for beam 3, we have the same moments and the reinforcement needed. And we could tell beam 2 has the greatest negative and positive moment. We have the greatest area still required to support the moment. Here's another view of our elevation view of floor 3, with beams 1, 2, and 3. We take a section cut at AA on beam 1 and beam 3, which shows us our L beam, and we see our 2 number 8s for the negative moments on top, enclosed by 2 number 3 stirrups. We take a section cut on beam 2 BB, we see our T beam, and we see our 3 number 10s enclosed by 2 number 3 stirrups. And now I'm going to pass the presentation to Marlon to talk about shear reinforcement.
Thanks, Howard. So the design stage, the next phase is to test for actual shear reinforcement. So based on the load calculations and the SAP analysis, it was evident that we needed to do some shear reinforcement. In this case, the shear reinforcement is from is for the clear spacing from face to face, and the configuration of stirrups is the first one at 5.5 inches with an additional 14 stirrups at 5.5, and then we have 7 additional stirrups spaced at maximum spacing at 11.5. So this totals at 22 for the first side of the beam, and since the shears are symmetrical on both sides, then the total beam has 44 stirrups. We chose stirrup number 3 for no. We just chose that one. If number 4 would have done the same, it would be actually less stirrups, but number 3 does the job. So this is beam number 2, and now the next phase is in this design stage is the development. Lucas got to cover.
So quick on the development length here. We did not need a hook. We have 2.5 inch cover space on all sides. No hook was needed. Our LDH was met. Our longest bar is 39 feet, 6 inches. We can't quite see it, so let me go ahead and just pull it over a little bit. All right, there's the end right there. You have your splice right here, 1.5 inch between this. Right here, we have 2 number 10 bars going into 4 number 10 bars. So the cutoff, not the cutoff point, but the point of inflection is right here. So the development length is met for the 2 number 10 bars right here. And this is what we have. We had the number 3 bar not needed for moment purposes, but needed for the stirrups to make sure that the stirrups have something to tie against. Elizabeth?
So for slabs, the purpose of a slab is to provide a flat horizontal surface in the building between the beams. And in our building, all of the slabs are one-way slabs, meaning that they're supported on all 4 sides with beams. And the slab that I'm going to talk about is one right there in yellow. So for slabs, we had to reinforce both in the longer direction and the shorter direction. And the way that we found the reinforcing bars, slide, is by using the maximum moment coming from SAP analysis, and that was negative 4.4 kip-feet. And from that moment, we determined that the main reinforcement running in the shorter direction should be number 5 bars spaced at 12 inches center to center. And for the temperature reinforcement, which is to resist cracks in the slab due to changes in temperature, it's to be number 4 bars spaced at 16 inches center to center.
Okay, thank you.
Sir?
For the columns, first thing I had to do was design the reinforcement, which measures from the load and the biaxial moments that occur in the building. First thing first, the column is constrained as a short column and a non-sway or braced frame. Taking those in consideration, we designed for the reinforcement of the column what we want